Welcome everyone to the 2024 Vision Spectra Conference. Thank you all so much for joining us, and in this session you will hear from Magnus, who has led the business unit industry at the Schneider-Kreuznach Group since 2021. Magnus kickstarted his career developing high-end optical lens and has a strong background in optics, mechanical design, and engineering. Today he's helping viewers better understand lens tolerance standards. If you have any questions or comments, you can type them right into the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me, Magnus. We appreciate you for taking the time to present at the 4th Annual Vision Spectra Conference.
Thank you for your introduction, Jacob. It's a pleasure to be here and a pleasure to speak at the Vision Spectra Conference 2024. Today, I'm going to speak a little bit about lens specification and how to make an educated decision on lens selection. There's lots more than just numbers of a lens and lots of misleading parameters that can be quite confusing for all of us. First of all, let me get you introduced to myself. As already mentioned, I started my career as an engineer after studying physical technologies and tested high-end lenses and optomechanical systems for industrial photographic and cinematographic applications, which gives me a strong technical background. And our field of industrial optics, strong technical background is needed to get used to customer needs and find the right solutions. Schneider-Kreuznach was founded in 1913 by Josef Schneider here in Germany. Our headquarters are still in Bad Kreuznach, Germany, and we have offices worldwide in Los Angeles, New York, Shenzhen, Hong Kong, and Singapore. On the left-hand side, you can see our building and the headquarters in Bad Kreuznach. You can see a little bit of our engineering works in the second image and quite a few pictures of our own production plant here located in Germany. We have fully vertically integrated manufacturing, starting with the development of lenses, starting from the optical design, which is basically a key aspect for us. Each lens starts with the optics, and our team of engineers is experienced in developing those optical designs. Nevertheless, we also need the mechanics, so we also do the mechanical design of our lenses in-house here in Germany. We have the full manufacturing line for components, optical and mechanical. We do the coating and we also do the assembly. Next to that, we have the quality inspection. All that are important parameters when it comes to specifying a lens and building high quality products. Let's jump into the topic of our talk today, misleading data sheets. We find this quite often that customers are coming to Schneider and present different data sheets when comparing lenses, and many information in these data sheets can be quite misleading. There's a lack of uniformity in the presentation of optical parameters. There's different standards in the different countries, but also different standards reaching back to photographic lenses that can be quite misleading in today's world of high-end industrial optics. All this can be quite a big challenge for you when selecting a lens and finding the right product for your application. This talk is designed to give you some feedback and some hints on what to look into and where you can easily be misled when selecting a product. All in all, when you select the lens, you probably run into different vendors and you have quite a big range of lenses you can choose from. Here's just a quick overview of different vendors, even though you will find a lot more, obviously. Next to Schneider-Kreuznach, we often run into Tamron, Koba, Ricoh, or Nikon lenses. But as said, there's many more, and there's a wide range of lenses to select from. Today, I want to give you an example of how to select the lens and then see where we can end up in the wrong direction. When we look into lens parameters, here's a quick overview of the main parameters that we probably want to look into. The basic parameters obviously relate to the image circle or the sensor coverage of the lens. In many cases, we see the camera or the sensor selected first. So this is basically a very key parameter to look into first. The second main parameter obviously is the focal length of the lens, defining the field of view. and basically the coverage the lens will see in the application. F number of the lens, which basically defines the opening of the lens, is another important parameter, especially when it comes to light throughput, but can also be quite misleading. Then we have obviously wavelength range. So there's different lenses designed for the visible range, for the infrared range. So obviously you want to have a match to have the right wavelength range of the lens for your application. What probably is not known as much is that most lenses are designed for a specific magnification. And there will be a fall-off in quality for different magnifications. So lens manufacturers will usually give you a magnification range of the lens, but be careful when doing this and when selecting a product. We'll see this at a later stage in this presentation. Last but not least, on the basic parameters, we have the lens and the camera mount, which obviously have to match, even though there's a wide range of adapters allowing us to use different mounts and attach a lens with different mount to a camera. When it comes to performance of the lens, you can see on the right-hand side the main parameters we see in terms of optical performance. Number one is modulation transfer function, which basically defines the sharpness of the image that you will see, and we will get into this during the presentation. Relative illumination defines the drop-off of light to the edge of the sensor, which again is an important parameter. Distortion can be quite important, especially when it comes to field of view. The transmission of the lens is another important parameter, especially when you are working in specific wavelength ranges, and obviously chromatic aberration, chromatic focal shift, and lateral color aberration define the performance of a lens. So what does this look like? Here's an example of a data sheet of our JADE 2.8 25mm lens. 2.8 is the F number of the lens, the 25 stands for the focal length. The C behind this stands for C mount of that lens, which is standard mount we see a lot in industrial applications. You can see a representation of our data sheet below this. It's 6 pages. Most of our data sheets are 6 pages. And they contain quite a few parameters. On the left-hand side, you can see basic optical parameters. The second page is giving modulation transfer function. Third page is giving additional information on distortion, relative illumination, and transmission. Then we have mechanical parameters like drawing of the lens to see the size and to see diameters and lengths of the lens. Also, you can see the mount here. And we also give information on accessories that might be necessary to adapt the lens to a camera, and a definition of parameters that are being used in this data sheet. So when selecting a lens, where do we start? Usually, what is known first is the object. What do you want to look at? You probably know the size of your object. You probably know what structures look like that you are interested to see. In most cases, it's a quality inspection application, so you probably have to see like small defects or specific features. But then again, there's a lot more restrictions when choosing a lens, like geometric restrictions in the total length between the object and the image. In many cases, we see restrictions to the working distance, which is the distance from the front of the lens to the object. In most cases, there's like a minimum working distance required for specific automation setups. And then, as I already said, in most cases, the camera is selected first. So we already have a sensor, which relates to sensor size, but also other parameters of the sensor. We have camera mount specified, and obviously the spectral distribution and the spectral transmission of the camera. And then, well, last but not least, usually customers go into selecting the lens when it comes to the F number, focal length, image performance. And well, speaking about this is a standard process, but what we would like to see as a lens manufacturer is look into the lens at an earlier stage, because sometimes you will find better solutions when selecting the lens first and adapting the camera accordingly to have a wider range of selection of lenses. Here's an example of how such a lens configuration can look like. And this is actually an extract of our website. In this example, we chose a working distance of 500 millimeters that is required for the application. And this is a 1.2-inch CMOS sensor. So we have an object width defined of 280 millimeters and an object height of 330 millimeters. With all the mathematics in the background that we don't want to go through here, we can calculate a focal length, and in fact our website does this for you. So we end up at a focal length required to match these parameters of 24.8 millimeters. The closest match to this would be the Jade 2.8 25 millimeter lens. So 25 millimeters is quite close to the 24.8 that have been calculated. Nevertheless, let's look into the details, what's happening here. Focal length is basically a marketing word again. And most companies apply an old DIN standard, which is a German standard, standard 4522, which allows for a tolerance of 6% between the nominal value of the focal length and the real focal length of the lens. So in this case, you can see on the left-hand side, as we call this 25 millimeter lens, that, well, it's not really a 25 because the effective focal length is 25.61 millimeters, so a little bit longer. And this can already cause quite a few problems. Additionally to that, obviously, manufacturing tolerances will have an effect on the focal length of the lens. Usually you can expect a tolerance of less than 1%. But then again, it's a change of focal length between lenses. So let's look what that means. We calculated the focal length of 24.8 millimeters for our application, resulting in a field of view of 280 times 240 millimeters. When we look into the nominal focal length of this lens at 25 millimeters, and we keep the working distance at 500 millimeters, the field of view is slightly smaller, about 2 millimeters on each direction. So you won't be able to capture your full object. Additionally, when we look into the real and effective focal length of the lens, which is 25.61 millimeters, the field of view shrinks down to 271 times 232 millimeters. And then we additionally have the tolerance in manufacturing. So we applied 1% here, resulting in like a maximum focal length of 25.8 millimeters, resulting in even smaller field of view. So what you need to do is increase working distance, if that's possible for your application, or select a lens of a shorter focal length, which can be tough to find because there's usually standard focal lengths you will find in the market. So probably the next smaller lens, smaller focal lengths will be in the range of 20 millimeters. Taking it on to the next parameter, which is the F number, another ISO standard applies, ISO 517. And this standard basically says there is 5% tolerance on the maximum aperture value. Most people confuse F number with the brightness they receive of a lens. But as we can already see, there's a tolerance for the F number. So when comparing different lenses with the same F number, you can already have different brightness of the image. Additional to that, the standard allows for bigger deviations when the aperture is stopped down up to 5.6. There's a deviation of up to 1/3 f-stop allowed, and when it goes to even smaller f numbers, even a deviation of half an f-stop is allowed. So this can be quite tricky when matching lenses and expecting the same light transmission. Also, when we look into the brightness of the lens, there's two more important parameters to stress, which is the relative illumination, which describes the light fall-off towards the edge of the sensor. So you will get that brightness in the center of the image, but each lens has a different light fall-off towards the edge of the sensor, and therefore you will see a darker image towards the edge of the sensor. In this case, even at open aperture, we have a light fall-off of only 30%, so you get 70% of the brightness towards the edge of the sensor, but still the image will be slightly darker. Additional to that, the transmittance of the lens is an important parameter. especially when comparing a fixed focal length lens to a zoom lens, which usually comes up with more lens elements. You will see lower transmission on a zoom lens and therefore less brightness of your image. So keep all these parameters in mind. It's not only the f number, but also the relative illumination and lens transmittance that really matter when it comes to image brightness. Next to that, when we look into field of view, we have the topic of distortion. Each lens basically has a distortion. Even the well-correct lenses still have a small geometric distortion, which will sort of bend the image. On the lower hand, right side, you can see on the left image like a perfect image with no distortion. The second image shows a barrel distortion, and the third image shows a pincushion distortion. This can be important when correcting distortion in software because you will see a smaller field of view and need to keep this in mind during the selection process of a lens. Another very misleading parameter that we see in many data sheets is the topic of TV distortion, which stands for tangential distortion. This is a very old standard and basically describes the distortion in tangential direction only, which is a different type of definition compared to the geometric distortion. For this example, for the Jade 2.8 25 millimeter lens, we will have a geometric distortion of 2.3%, whereas the TV distortion is 1.1% only. You will see many suppliers only mentioning TV distortion with specific lenses, as this value is smaller and gives a better impression. But still, if you compare different standards, you won't come to the same results. When we look into a wide angle lens, like our Topaz 2.4 6.5 millimeter lens, the difference is even more significant. The geometric distortion of this lens is 11%, which is quite common for a wide angle lens, whereas the TP distortion is only 1.8% and can easily lead you to the interpretation that this lens has a lower distortion, whereas it's just a different standard. Let's move on to modulation transfer function. And before looking into the pitfalls of comparing modulation transfer function, let me give you a brief introduction into what modulation transfer function stands for. You will usually find modulation transfer function representations in every data sheet. However, representations can be quite different for different manufacturers. On the right-hand side, you can see what we are doing here at Schneider-Kreuznach. We usually give 9 MTF plots. This is the MTF versus field, and this is given for different f numbers and for different object distances, which obviously result into different magnifications. Next to that, we state the spectral weight this MTF has been calculated for, which can have a significant impact on the way MTF looks like. As a short form, MTF is basically giving a contrast. So when we look into the left-hand side image, we can see test patterns at different spatial frequencies, excuse me for that. Usually the higher spatial frequencies have a lower contrast. So what MTF says is we look into the contrast, we have a perfect image or object basically of high contrast, and what the lens transfers on the other hand side. And you can see this behind the lens, where you can see no perfect contrast anymore, especially on the higher spatial frequencies that is represented on the right hand side. And below this, you can see MTF representation that is very common in the Americas, where you can see modulation transfer function versus the spatial frequency, which is giving you an idea of the image quality. One of the main terms that we see here is line pairs per millimeter. This is basically the spatial frequencies that are being used for the representation of MTF. Don't be confused by lines per millimeter. We can see some manufacturers giving LPMM without line pairs per millimeter. So they basically trick you and they get you lines per millimeter, which basically doubles the contrast, so to say, when you're not careful. because they simply state half the spatial frequency. Another important aspect of MTF is that we have two orientations, radial and the tangential orientation of structures. This is important because you will see those two MTF values in basically every data sheet. And in some applications, specific orientations are more important than others. Usually, the radial orientation is given with a solid line in the MTF plots, whereas the tangential orientations are represented by a dashed line. But even this doesn't really have a standard because there was an old German standard which mixed this up. And some manufacturers are still mixing this up. Some simulation software is still using different representations. So be careful when looking into radial and tangential orientations and MTF plots. Here's another representation of MTF and the different plots that are being shown in data sheets. The left-hand plot is the MTF versus field, which is the most used plot here in Europe. Usually MTF is given for different spatial frequencies. In this example, we use 20, 40, 80, and 120 line pairs per millimeter. On the horizontal axis, you see the width of the sensor, and on the vertical axis, you see the MTF. In this case, it's represented as modulus of the OTF, which is just a different term for MTF. The second plot is more used in the Americas, which is the MTF versus spatial frequency. So each line represents a different image height, whereas contrast is given for all spatial frequencies. And the right-hand side is an even more detailed plot. This is giving through focus MTF. So this shows the MTF in different focus positions. However, this plot can only represent one spatial frequency, and in this example, we use 80 line pairs per millimeter. What are the important parameters that influence MTF and can be quite misleading when comparing data sheets? As already mentioned, we have the spectral weight, so which illumination is being used, what is the spectral sensitivity of the sensor. This can influence MTF significantly. The working distance of the lens or the working distance of your application will have a strong influence on the MTF. The F number, the focus position of the lens, the spatial frequencies we look into, and also the field height have an important influence. We will look into each of these parameters on the next slide. And I'm sure some of the plots will really surprise you as the differences are quite significant. Again, we selected our Jade 2.8 25 millimeter lens for comparison. On the left-hand side, you can see the MTF versus field plot for what we call white light. Usually, our spectral distributions being used represent broad white illumination, like you have with an LED illumination that's being used in most industrial applications. On the right-hand side, this is exactly the same lens, no changes to the lens, just a difference in the illumination spectrum. And we basically use a narrowband green LED here, and you can see a significant improvement in MTF. When we look into the red line here on axis, you can see on the left-hand side a contrast of maybe 55%. On the right-hand side, you can see a contrast of maybe 68%. So you can see how the spectral weight really has a strong influence on the overall image quality, making it important to look into the spectral distribution. Most lens manufacturers won't give you the spectral weight being used for their MTF simulations. So this can be quite tricky when comparing data sheets of different manufacturers, because in fact, you don't really know what you are comparing. Second parameter we are looking into here is the working distance. As already mentioned, most lenses are designed for a specific working distance. And in our industrial imaging lenses and the machine vision lenses being used for quality inspection, usually we have a rather limited working distance. Range of 500 millimeter is something very common, and this is what we see on the left-hand side. Now, if you want to use this lens for a different application, look into objects far away from the camera, you can see a significant impact on the MTF, especially with this lens, the MTF is dropping down towards the edge of the sensor. Keep this in mind when comparing lenses, because in the end, you have to look into the working distance or magnification you're using the lens for to make a good guess and a good educated decision which lens will yield the best performance. Another parameter is the f number. We see customers stopping down lenses significantly. So we have the representation of MTF for f number 4 on the left-hand side here. On the right-hand side, it's the same lens, the same focus position for f number 11. In this case, diffraction kicks in, and we see a significantly lower MTF performance. In some cases, going back to the f number, lens manufacturers won't give you the MTF for full open aperture, but only will show you a stop down MTF, which can be quite misleading. So the next example goes to the focus position, and this is also quite important of how you focus a lens. Usually you can focus a lens towards the center or to focus it to have uniform performance over the entire image field. And this is what we usually do. We focus our lenses in a way to have uniform performance over the entire image. On the right-hand side, you can see the exact same lens focused to best performance on the center of the image, which leads to higher contrast on axis, whatsoever lower performance in the field and towards the edge of the sensor. Another very common topic is the topic of spatial frequency. Many manufacturers will give you low spatial frequencies because the right-hand side plots look really nice, very high contrast. When we look into detail, it's 5, 10, 20, and 40 line pairs per millimeter, whereas the left-hand side shows significantly higher spatial frequencies, coming up at a lower contrast. But then again, this is what you want to look into in real life. So don't be misled by marketing words and marketing people showing you high contrast and low spatial frequencies. Another very common topic is the field height you're looking into. So we chose the same lens to be used on a smaller sensor on the right-hand side. And in this example, MTF obviously looks better. In many cases, it makes sense to use a lens for a smaller sensor, as you will get a very uniform performance over the entire sensor. But you really should look into the image field heights represented on the MTF plots to make a good comparison between lenses. So the next topic in here is the MTF versus production. And this is something nobody is telling you. Basically, what you're buying is a simulation of the lens. And it only gives you the nominal values of MTF, but people won't tell you about the fall off of quality in production. So in this example and this slide, you can see on the left-hand side the nominal MTF performance of a lens. And on the right-hand side, you can see 3 measured lenses that show quite a bit different performance. So looking into the first lens, you can already see there's a minimum small fall off towards the center of the image, but overall the performance looks pretty much the same. And you can see this especially good on the 80 line pairs, which is the red lines here, which show the most impact. When you look into the second image, you can already see a significant fall off on the center of the image. Maybe something like 5, 6, or 7% in MTF. And on the right-hand side, on the third image, you can see a fall off in quality towards the edge. All this is in a range of, let's say, 5 to 10% in MTF. You will find a lot of lenses in the market with significantly higher deviations from the nominal performance. And with all the tricks that we already saw on MTF, many manufacturers will lead you to think they have a good lens. But in fact, when you test the lens, you will see quite a different performance in your application and also in terms of quality between lenses. Here at Schneider, we have very strict quality standards in our production to make sure lenses perform uniform along the field, but also along production, so that the deviation from the nominal MTF values is kept small. So here's a quick summary of what we already said on MTF. Datasheets only represent the nominal lens performance. The manufacturing tolerances and the as-built quality is kept as a secret for most manufacturers. And you probably won't find out without asking your manufacturer what the quality is that you can expect from the build system. The quality spread on serial production can be a big issue in many applications. If the one lens is performing significantly better than the next lens, this can lead to quite a few problems, especially when it comes to detecting defects in production, because the one lens will see the defect, the other won't. So be especially careful when comparing lenses and only testing one lens of each manufacturer, because you will never be sure that the next lens shows the same performance. The spectral weight in simulations is often kept as a secret, and this should already guide you to the question, is this really the performance of the lens, or is this more of a marketing datasheet? Most other parameters are often not clearly communicated, like which working distances are being used, what is specific restrictions to the quality of the lens and to the MTF. And some manufacturers will even try to misguide you and showing different spatial frequencies at different field positions, maybe even different working numbers to make the data sheet look good. So be very careful when selecting lenses. So as a summary of this talk, which can only cover a few topics, obviously, as there are many other topics that could be discussed and many other parameters that can be quite misleading. But the main parameters here is that there is significant tolerances on the F number of up to 5%. There is significant tolerance on the focal length of up to 6% allowed to current standards being used. And usually when it comes to wide angle lenses, it's easier to have a longer focal length. So most manufacturers will use those 6% to make a longer focal length for the build lens. And also it's easier to build a lens that's stopped down a little more. So many manufacturers will use that tolerance for F number as well. Distortion, well, there's also different standards and no direct comparison is possible in some cases. Modulation transfer function as the main quality parameter to lenses is an important parameter, and it's a very good representation of the image quality. But as said, you should be very careful on comparing MTF between different lenses. So here's our 6 tips for choosing your next lens. Be aware that there are no real standards, and there's really a lack of standards of how to represent lens performance. Be careful when comparing. Don't trust the marketing terms. Even the marketing team in here agreed to that. We try to keep our data sheets as technical as possible, but don't fall into marketing terms. Don't be misguided by manufacturers telling you this is a 50 megapixel lens. Technically, the lens never has a megapixel count. It's a sensor having the megapixel count. And the image performance strongly depends on the application, on parameters like spectral distribution, working distance, F number being used. So this can be quite confusing. Don't be misled by generic terms that are not really defined well in the data sheets. Even ISO and DIN standards are not reliable in all cases, and many standards result back from photographic applications, which make it difficult to be applied for modern high-end industrial imaging applications. As said, pay attention to the details when you are comparing data sheets between different manufacturers, as the comparison can be quite difficult. So always ask your manufacturer detailed questions in case of doubt, and you will find more details from the manufacturer. From our point of view, new standards are required for industrial optics to make it easier for consumers and customers to compare lenses and to have a better representation of technical parameters. Thank you for your attention for my discussion on misleading data sheets. If you have any questions to this, feel free to contact me. On this last slide, we're showing my contact information. Me and my team will always be there to help you, and we are looking forward to your feedback and possible questions.
Thank you so much, Magnus, for joining us to help educate viewers on the importance of lens specifications. Just to echo your statement here to everyone joining us in the audience, you can either reach out to Magnus directly on the contact information provided, or you can submit your questions on the conference chat box that is available right on your screen. And do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we hope you're enjoying the 4th annual Vision Spectre Conference. Thank you all so much for joining us.